So we have seen an example of how the interrupt interrupt handling can be done in the context of the smart timer. So as you can see, these are some common patterns that you are likely to encounter when we are dealing with interrupts, right? So for example, I could say that I want to, rather than waiting for one interrupt to happen, maybe I'll say, wait for n of them to come, right? One possibility is, I don't want the keyboard, right, every time I press a key to go and sort of bother everybody and say, okay, this is what happened. But I could say maybe, every time I get like some 5 or 6 characters, wake up and do something, right? So I could very easily say wait event interruptible and check whether that goal has been met. I have got enough characters waiting in my buffer, right? I could also instead have something called a timeout. I could have a interruptible wait on interruptible, but with a timeout. So remember that this is a different function. It's wait event interruptible, but with a timeout. What this means is wait for the condition, right? This is the wait queue. This is basically, the WQ is that st-wait that we used, right? The pointer there. So wait on this wait queue. This condition is something like this, right? It could be set a goal and tell me whatever it is. This condition has to be some Boolean expression that can be evaluated. But there is a third parameter, right, which basically tells me how long to wait, and that if I don't sort of get to this value within a certain amount of time, I just exit anyway, right? And the way it handles it is if this function returns the value 0, it basically means that the timeout is what happened. Okay, so it's a clear way of sort of saying, okay, wait for maybe 10 or 100 milliseconds for somebody to respond, or maybe for a key to be pressed, or for a button to be pressed, or something of that sort. And if it doesn't happen within that time, go do something else, right? Don't continue waiting over there. One interesting sort of helper function that you will notice over here is this thing called msec to jiffies. Msec over here is milliseconds. A jiffy is a strange unit of time, right? You might have heard the term wait a jiffy or something of that sort. It's an sort of undefined unit of time. It's not a formal physical unit of time, right? You actually are trying to wait for a certain number of milliseconds, right? And in this case we want to wait for 10 milliseconds, right? The problem with it is it turns out that the kernel needs to handle things differently. We normally, when we are dealing with things at the kernel level, we don't directly specify things in milliseconds, and this is for a number of complicated reasons. One of them is the fact that each computer that you are running on could potentially be running with a different clock, right? And not only that, the clock itself could sort of vary at runtime. So to account for all of that, there is this internal notion of time that is maintained by every system, right? Because otherwise I can't even keep track of what it means to say 10 milliseconds, right? So rather than just directly trying to say, okay, I'll wait for so many clock cycles, what we say is take this particular thing, convert it into some other unit which can be easily counted or tracked inside the kernel, right? If you think about it, this is not really necessary. I could just as well have said, give 10 as the parameter over here, and inside this function I could have done the conversion into whatever other parameter that I want, right? You might think about it, right? When I actually say sleep for 10 milliseconds, it's not as though it's actually going and sleeping for 10 milliseconds. That sleep function will take the value 10, convert it into some appropriate number of clock cycles, put a counter over there and say, okay, have I reached that particular number of clock cycles, and then exit. The number of clock cycles will have to be determined based on the duration you want to wait and the frequency at which your clock is running. So this conversion to jiffies is just sort of a helper function, right? What we do is we basically say, okay, up front I can convert it into some other format that is easier for the kernel to handle, right? And this jiffies turns out to be something that is an internal unit of time used by the kernel. So anyway, the milliseconds to jiffies is something which is done as a standard sort of conversion process. It depends on what is the real-time clock that is being used internally by the system, right? So in this case, as far as the Linux kernel is concerned, they have put the requirement that you need to explicitly convert into the appropriate number of jiffies that I need to wait, so that I can then go ahead and wait for that long and then move forward from there. Okay, so the point is both of these are common patterns that you are likely to see. I can have any kind of goal setting that I have over here, and I could also have a timeout based approach. Now, before we get to the handling of the FIR filter, there is a notion of something called a lock, which is worth understanding, right. Once again, locks are primarily required, most of this, right, the idea of atomic operations, locks, all of these are related to this notion of something called synchronization, right. And synchronization basically says there are multiple things that are happening in different places. How do I make sure that two of them don't sort of end up trying to modify the same thing at the same time, right. It could be one particular value which is written in memory. I already gave the example of an atomic operation. I don't want one processor to go and read a value, meanwhile the other processor comes and modifies it, right. And this kind of thing can happen in multiple different contexts, right. So what we do is we implement something called a lock, right, and the most general version of a lock is I should be able to call a particular function over here, right, in my code, and I basically call it with this some variable or value over here, which I have given the name mylock, right. In this case, of course, I am using a pointer to mylock, but yeah, in general, what I am doing is I am basically I need to have some parameter that I can change or set, I can control. And the way that we usually do this is I want this taking control of my lock to be an atomic operation. I want to make sure that while I am taking control of my lock, nobody else can do it, right. And the typical way that I would do something like this is I would go check the value of my lock. If the value is 0, I immediately increment it to 1, and then I proceed into the next part of my code. If the value is not 0, I go away and come back after some time, right. I do not proceed, I wait over here in this line, okay. So that's what we mean by saying this line blocks here until the lock is acquired, okay. So if I have some way of sort of testing the value of my lock, and if it is satisfying a condition, like if it is 0, I immediately increment it, right, then I can be sure that anybody else who is also trying to lock on my lock, right, the moment I lock it, nobody else can do so, because anyone else who looks at that value will see that it has now become the value 1, okay. So correspondingly, so what that means is whenever I get past this particular line, right, as you can see from this comment, the code only reaches here after successfully getting the lock, right. So I can only reach this particular point after I have passed through this particular statement, right, which means that at that point my lock no longer has a value that others will be able to capture. So that's good. It means that if I want to go and make some modifications to some sensitive variables over here, provided that whoever else is trying to change it is also sort of looking at the same lock, I can be sure that no one else is going to go and change those values. This is usually called a critical section, right, because I want to protect it. I want to make sure that whatever changes I make here are done in such a way that nobody else could be changing them at the same time, right. So this function that I have written as critical section over here is what is called protected code. It is protected by this lock, right. At any given point in time, only whoever holds this lock will be able to change it. Now what that also means is after I am done with my critical section, I should unlock, because if I don't, nobody else is ever going to be able to proceed, right. All the other functions who are waiting for that particular lock are going to be stuck. So I can protect certain sections of code only after getting the lock can we do this. Any other thread, right. So I have not really spoken much about the notion of a thread. You are broadly familiar with the idea of threads from, let's say, something like even the embedded C programming, right, where we can have multiple different and you could have task threads that are running, right. So even an RTOS would have the notion of different threads of execution or tasks that can run concurrently. In the context of an RTOS, of course, it's usually what is called cooperative multitasking, where each task sort of gets up to a certain point and then says, okay, I don't have anything further to do here, now you take over and assign the work to someone else. But there's a scheduler that's sort of going around and saying, okay, who's next, who's next, who's next, and running different tasks. In the context of something like a Linux kernel, it's the same thing. There are multiple functions that need to run. A thread is a thread of execution, a set of functions that are being run, right. And what that means is I could basically be jumping between different threads. Maybe I spend a certain amount of time, 10 milliseconds on one thread, then 10 milliseconds on another thread and so on. I'm jumping between them fast enough that as far as the user is concerned, they can't tell the difference, right? Or I could have one thread running on one processor and another thread running on another processor. Ultimately, what it means is any thread that needs to make a change in this critical section must first acquire the lock. If it doesn't get the lock, it has to wait. It would most likely sort of go to sleep and be woken up by the kernel when the lock becomes free. Okay. Now, how exactly do we implement this? This is the same as the atomic operation idea, right? In particular, there are usually support from machine level instructions. So, there is something called the compare and exchange operation on x86 processors. There are these exclusive load and store operations which are on ARM processors, etc., which allow you to make sure that you are able to load, modify, write, right? Read, modify, write is a common sort of pattern that's used over there, and do it in such a way that you can basically acquire a lock. And releasing the lock is much easier. All that you need to do is basically, convert it back to 0, and whoever else wants, and only after that point somebody else can acquire the lock. So that's a much simpler thing to do. So these locks become important. Let's see how exactly they are used by taking some examples in the context of the FIR filter demo. Now, before I get into the second demo, I just want to also talk about two kinds of locks that are commonly used in concurrent programming. So whatever I mentioned right now is a notion of what is called concurrent programming. The moment you have different threads available in a system, they are operating concurrently. So what does operating concurrently mean? It means that they don't really depend on each other, right? Any one of them could be executed. After some time I could switch over to the next one and so on. So there's a difference between concurrency and parallelism. This is not the same as parallel execution. Parallel is only when you actually physically have two processors and they are running at the same time. Concurrent just means that they do not have dependency. If they are concurrent, they can be run in parallel, but not necessarily the other way around. Okay. Alright, so a mutex is something which comes into play in concurrent programs, right? What we do usually is that we set up some kind of a flag or a counter which indicates the lock state, right? So just like I had this example out here where I need to lock, I would use some kind of a flag to indicate the lock state, and I would set up a wait queue in my operating system for threads that are sleeping on this lock. Okay. So what that means is, supposing many different threads have this thing where they say lock on my lock, right? I could have maybe 2 or 3 or 5 or 10 or 100 threads, all of which are trying to wait on a particular lock. An example of that might be maybe all of them are trying to write data into a network card, but only one of them is allowed to write at a given time, right? So they all try to take that lock. If whoever gets it is able to go ahead and do something, all the others have to wait, right? Now, rather than just sitting over there and going on checking the status of the lock, what is actually done in practice is the operating system keeps a queue, right, which says, okay, who are all the functions who are waiting for this lock? And as and when the lock becomes free, it wakes one of them up and says, okay, do you want the lock? If for some reason that has decided you have cancelled the lock, or you have gone somewhere else, or it's timed out or something of that sort, then maybe it's not there, you go wake up another one, the operating system takes care of that, right? But ultimately it can sort of make sure that there is a certain degree of fairness and so on that's associated with it, and the threads will be woken up as required without necessarily putting the CPU to a lot of load. And what that means is, since you have to either block or wake up threads, we use some kind of system calls. These are functions which go into the kernel and basically are able to wake up whatever is the thread or function that is required at the right time. Now there is another way of doing things which is called a spin lock, right? A spin lock is actually what's called a busy wait loop. It essentially gets implemented something like this, right, where it says while test and set lock value is not equal to 0, wait. So here's the crucial difference. I told you that in the case of a mutex, if I don't get the lock, I'll just go into the wait queue and go to sleep. Spin locks do not do that. They are basically sitting in a while loop, constantly testing the value again and again and again until it has got satisfied, which means that they are actually burning CPU cycles while waiting. But the advantage is that there is no question of an arbitrarily long sleep, right? They can be done like this only in a context where you are sure that this condition will be satisfied fairly quickly. So anybody taking a spin lock is also expected to finish that spin lock and get out of it fast, right? The good thing is, because you are doing this test over here, you don't have extra latency. You don't have to wait for the OS to wake up, you don't have to register the event, to then go check the queue value, to then wake up the thread. All of that doesn't happen. The thread is constantly just waiting for something to get free, and the moment it gets free, it basically jumps in and starts doing its work, right? This is usually how IRQs handle things, right? So inside an IRQ, you do not want a mutex, because if I go inside an IRQ and then I go to sleep because I don't get the lock, all kinds of bad things can happen, because I am now inside an IRQ handler. During that time, if another IRQ comes along, it can very rapidly complicate things and lead to deadlocks and other kinds of undesirable behavior, right? So what we do instead is that inside an IRQ handler, we use only spin locks. In fact, we go one step further. There is a version of the spin lock which is also IRQ safe, right? So what this does is, it basically calls a spin lock like this, but it also saves the present state by basically disabling all other IRQs. What it says is, I want to do this lock, critical, and then unlock. I take a spin lock over here, which means that I expect to get the lock very quickly. During that time, I am also turning off any other interrupts, which means that the CPU is not going to get interrupted, nothing else is going to happen during this time. As soon as I get this lock, I go finish up my critical code quickly and unlock it, right? By using the IRQ safe version of spin lock, you can be sure that you are not going to get interrupted while you are already inside an interrupt handler, and it's generally a safe way of handling things. But this is important. It is possible to write code where you use a spin lock instead of a mutex, right? Usually it would be a bad idea, because it would mean that you are basically burning CPU cycles and keeping the processor busy, not particularly doing anything useful. It's also possible to write code such that you use a mutex where a spin lock makes sense inside an IRQ handler. It's also a terrible idea, because your mutex might go to sleep, and during that time you might end up getting another IRQ, or if you have disabled interrupts, it basically means you could just completely get deadlocked because you went to sleep and then never woke up again, right? So where do you use a mutex, where do you use a spin lock? In our context, there are some simple rules of thumb, but in general, in order to understand it fully, you need to go deeper into the notion of how concurrent programs are written. Okay. So like I said, for what the kind of purposes that we are using, right, we basically want an IRQ and a separate processing function, a thread, which is going to handle the data. What we do is we basically call the spin lock IRQ save. We have a small critical section out here, and then we spin unlock, right? What does the unlock do? It basically also allows new interrupts to happen, right? So spin locks are used in this way. Mutexes are used for process only paths. What do I mean by process only? It means that there is something more long term, things like maybe reading or writing to a file, copying data from one place to another. They are processes, they are not IRQs. If one of those processes gets interrupted, it's still okay. It just means it will take a little longer to execute, but it's all safe, meaning that it can actually go to sleep, wake up after a little while and continue its work, and things should be fine. The simplest rule of thumb that we need to follow: never take a mutex inside an IRQ handler, right? The IRQ handler, in terms of terminology that I had briefly mentioned earlier, is effectively what's called the top half of the IRQ, right? It is the part which is responsible for immediately responding to the IRQ, and we want to keep it as brief and as quick as possible.